So the continuation of last class, we are going to discuss about temperature rise. So while you are calculating the temperature rise of the machine, you should consider these all parameters. Q, that is the power loss, G, weight of the machine, then H, specific heat, and S is the cooling surface, and lambda is the cooling coefficient, and C is the cooling coefficient in terms of lambda, then the temperature rise and the maximum steady state temperature during the heating process, then steady state temperature rise during the cooling process, then initial temperature, theta is the initial temperature, then theta TH, that is the heating time constant, TC cooling time constant. So we are considered as the smaller time interval, that is the dt. So the total heat developed in the machine, that is the total heat with respect to the time, then total heat stored in the machine, the weight of the machine, then specific heat, then the temperature rise. The temperature rise also small because we are considered smaller time interval. Then heat dissipation, it should be considered as cooling surface and cooling coefficient and temperature rise as well as the time. So yeah, so we are considered for these three equations, that is the total heat developed, it should be equal the sum of these two. So we are obtained the expression Q into dt, that is the total heat developed, it should be equal total heat stored and total heat dissipated. So the total temperature rise, then there is no further temperature rise because of once the machine reaches the maximum steady state operating temperature, after that there is no further temperature rise. So we can consider the theta m is the maximum steady state temperature during heating. At the time the T should be infinite because after reaching of steady state temperature there is no continuous increasing temperature is not possible. So the time we can consider as infinite. Okay. So we can rearrange this expression. So once the maximum temperature is rise, so that we are considering this expression alone. So from that we can find it out the maximum temperature rise. It should be theta m, it should be equal the Q divided by S lambda. Okay. The Q is the total heat and S is the cooling surface and lambda is the cooling coefficient. So we are obtained the equation 6, that is the maximum steady state operating temperature. So then we are considered another one thing, that is this is for the heat energy stored. The heat energy stored, it should be equal to the, again we are rearranging the equation 4, we can obtain this equation, that is the Q into dt minus, while we are moving the equation from LHS side to RHS side, we can rearrange this expression and finally we got this. So in this expression, the commonly we can have the small dt, we can take it outside, then we are obtaining the expression for d theta by dt, then we are rearranged, then we are segregated this expression, finally we achieved Q divided by SH minus S into lambda into theta divided by GH. So once you are using, if you are not using any of cooling medium like cooling surface area or cooling coefficient, when the options of cooling medium, the S value is 0. There is no heat dissipation occur. So S value we are considered as 0. If your S value is 0, this term is again, it may convert like that, d theta by dt, it should be equal to Q divided by SH, that particular term, this alone it will come. So it is getting 0. So finally we are again rearranging this expression and we are obtained the Qt, it should be equal to GH into theta, right? So if you are considered the heating time constant, here available time is T. So if you are considered T was heating time constant, the T we can replace TH. Similarly, the temperature rise, that was the maximum temperature rise. If you are considered theta, you can rearrange theta m. So you can rearrange this expression again. Q into TH, it should be equal to G into H into theta m, because here theta is the theta m. So if you are added this value, so finally you are adding already we are obtained that lambda m, that maximum steady state temperature, lambda m we obtained, that is the equation 6. So from the equation 6 again you can substitute here, then you can obtain the heating time constant T, it should be equal to G H divided by S lambda, that is the equation 11. Okay.